In this video, we're going to talk about the hyperbolic functions, also called hyperbolic trig functions. So the hyperbolic functions have the same relationship to a hyperbola as our trigonometric functions do to a circle. So we know for our trig functions, here's a circle. This is x squared plus y squared equals 1. Then a point on the circle, xy, is given by cosine of t and sine of t. Now, if I look at a hyperbola, x squared minus y squared equals 1, that looks like this. Now take a point on this hyperbola. This point is the hyperbolic cosine of t, hyperbolic sine of t. We denote the hyperbolic functions with very similar notation to our trig functions. We just put a little h after it. So we have hyperbolic cosine is cosh, and hyperbolic sine is sin-h. So let's actually write down the definitions of our hyperbolic sine and our hyperbolic cosine. So here's our definitions. First, the hyperbolic sine of x is defined as e to the x minus e to the negative x all over 2. And the hyperbolic cosine is e to the x plus e to the negative x all over 2. And our remaining hyperbolic functions can all be defined using the same sorts of relations that we're used to with our trig functions. So, for example, our hyperbolic tangent is equal to the hyperbolic sine over the hyperbolic cosine. Which would be equal to e to the x minus e to the negative x over e to the x plus e to the negative x. We can get all of the others using similar properties. I'm just going to give us the definitions. We have our hyperbolic cosecant is 1 over hyperbolic sine. We have our hyperbolic secant is 1 over hyperbolic cosine. And the hyperbolic cotangent is hyperbolic cosine over hyperbolic sine. And of course, these three can also be written differently using the definitions of hyperbolic sine and cosine, using all the e to the powers. So just like our trig functions, hyperbolic functions also satisfy a lot of identities. I'm going to give us a huge list of hyperbolic identities that might come in handy sometimes. Whether you choose to memorize them or not is up to you. I personally do not have all of these memorized. I just know I need them at certain times and look them up when I need them. So here's a list of some of our hyperbolic identities. First, hyperbolic sine of a negative x is equal to negative hyperbolic sine of x. Hyperbolic cosine of negative x is equal to just hyperbolic cosine of x. We have, here's one, hyperbolic sine of x plus y is equal to hyperbolic sine of x, hyperbolic cosine of y, plus hyperbolic cosine of x times hyperbolic sine of y. One that's kind of similar to that one is the hyperbolic cosine of x plus y is equal to hyperbolic cosine x times hyperbolic cosine y plus hyperbolic sine x times hyperbolic sine y. And then we just have three more identities that are fairly common, and these are the ones that I remember the most. We have the hyperbolic cosine squared minus the hyperbolic sine squared. Forgot to write my h. There we go. Is equal to 1. That one's similar to our sine squared plus cosine squared equals 1 from trigonometry. It's just we have a minus sign in there when we use our hyperbolic functions. But it's very similar to that one. Another common identity, 1 minus the hyperbolic tangent squared is equal to the hyperbolic secant squared. And hyperbolic cotangent squared minus 1 is equal to hyperbolic cosecant squared. So those are some of the most common identities. There's others out there, but I just wanted you to see some of them. They come in handy sometimes when you need to simplify things involving hyperbolic trig functions. Now, of course, this though is a calculus class, so we need to learn how to do calculus with these hyperbolic functions. We're going to learn the derivatives of the hyperbolic functions. We are going to learn about inverse hyperbolic functions and their derivatives. And we're going to just practice doing a bunch of derivatives and eventually some antiderivatives involving these hyperbolic functions. So derivatives of hyperbolic functions. The first one, the derivative of the hyperbolic sine is equal to the hyperbolic cosine. That's super nice because that is the same sort of relationship we have when we take a derivative of just our regular sine. We get cosine. Now this one I'm going to actually show us. Now we know that to calculate this, here's my proof. The derivative with respect to x of my hyperbolic sine, well, hyperbolic sine was defined as e to the x minus e to the negative x all over 2. If I take this derivative, well, I have 1/2 that's multiplied in the front. Derivative of e to the x is itself. And then the derivative of a minus e to the negative x, we need a chain rule. We get itself times the derivative of its exponent, which is -1. So I'm going to get 1/2 times e to the x plus e to the negative x, which that is e to the x plus e to the negative x over 2. That is the definition of hyperbolic cosine. So it works just using our standard derivative rules. Now, so that's our first one. Derivative of hyperbolic sine is hyperbolic cosine. So now my question that I would ask you, if you could answer it, would be, what do you think the derivative of hyperbolic cosine is? And my guess is if we were in a face-to-face class, you'd probably tell me a negative hyperbolic sine, thinking it's going to match our trig derivatives. And unfortunately, that's not quite right. The derivative of hyperbolic cosine is just hyperbolic sine. It's not negative hyperbolic sine. So let me prove this one for us really quick. If I'm taking the derivative of hyperbolic cosine, we need to take the derivative of e to the x plus e to the negative x over 2. Well, I'm going to have that 1/2. Derivative of e to the x is itself. And then for e to the negative x, it's a chain rule. We get itself times the derivative of its exponent. And the derivative of the exponent is -1. So that changes it to a minus sign in the front there. But then what's this? Well, that's exactly equal to e to the x minus e to the negative x over 2, which is our hyperbolic sign with no negative sign in the front. So we do not get derivative of hyperbolic cosine as negative hyperbolic sign. We don't have that negative like we do with the trig functions. Now, I'm not going to prove all of these, but they are pretty straightforward to just prove them using the definitions of the hyperbolic functions. But here are the other derivatives for us. The derivative of hyperbolic tangent is the hyperbolic secant squared. That one matches like what we would expect with our trig. The derivative of hyperbolic cosecant is negative hyperbolic cosecant times hyperbolic cotangent. That one's also nice because it matches what we would expect based on our knowledge of just regular trig functions. The derivative of hyperbolic secant is equal to negative hyperbolic secant times hyperbolic tangent. That one's not so nice. If that didn't have a negative sign in front of it, it would be exactly like we would have expected using our trig knowledge. But we do actually get a negative sign that shows up, which you can check by just taking the derivative using your derivative rules. And the last one, the derivative of hyperbolic cotangent is negative hyperbolic cosecant squared. So most of these are just like our trig derivatives. The only two that are a little bit funny is the derivative of hyperbolic cosine and the derivative of hyperbolic secant. They had the opposite sign of what we would have expected. But all of the others are what you probably would have predicted. Now let's define some of the inverse hyperbolic functions. I'm not going to define all of them, just the three most common. Our hyperbolic sine inverse is defined as the natural log of x plus the square root of x squared plus 1. And this is defined for all x in the real numbers. The hyperbolic cosine inverse is the natural log of x plus the square root of x squared minus 1, and we need to have x greater than or equal to 1. And then the hyperbolic tangent inverse is 1/2 natural log of 1 plus x over 1 minus x. And this is defined for x that are between -1 and 1. And there are definitions for all the other hyperbolic inverse functions, but we don't really use them as much, so I don't bother listing them here. These are the three most common ones that we see. Now, let me give us a list of all of the derivatives of the inverse hyperbolic functions, and then we'll finally move to some examples using all of this knowledge. the derivatives of inverse hyperbolic functions. First, the derivative with respect to x of the hyperbolic sine inverse of x is 1 over the square root of 1 plus x squared. Now this can be found by actually calculating it using the definition of the hyperbolic sine inverse and just using our derivative rules. In particular, you'd be using a couple of chain rules to get to this answer. What the value is of possibly memorizing these derivatives is, well, imagine that you have an integral that has a 1 over square root of 1 plus x squared in it. Well, now you'll know that the antiderivative of this should be the hyperbolic sine inverse. The derivative of the hyperbolic cosine inverse is 1 over the square root of x squared minus 1. And the derivative of the hyperbolic tangent inverse is 1 over 1 minus x squared. So again, all of these could be valuable if you have to find the antiderivative of the other side of the equation. You'll know which hyperbolic inverse function it corresponds to. Now, I personally actually prefer not doing this by memorization. I prefer using a technique that we're actually going to learn in a couple of videos. So I would suggest that maybe try to commit some of this to memory, but don't freak out too much if you can't memorize it at all, because in a couple sections we'll be moving on to a technique that will let you derive all of these without memorization. The derivative of a hyperbolic cosecant inverse is -1 over the absolute value of x times the square root of x squared plus 1. The derivative of hyperbolic secant inverse is equal to -1 over x times the square root of 1 minus x squared. And then our last one, the derivative of hyperbolic cotangent inverse of x is 1 over 1 minus x squared. So now we're finally ready to do a couple of examples. First example, find the derivative of hyperbolic tangent inverse of sine of x. Now, think back to your Calc 1. Even though you didn't do hyperbolic functions in there, this is going to be a chain rule problem because I have a sine of x plugged into a hyperbolic tangent inverse. So I need to do the derivative of the outside times the derivative of the inside. Now, the derivative of hyperbolic tangent inverse we just had was 1 over 1 minus x squared. Now, I don't just have an x inside my hyperbolic tangent inverse, I have a sine x. So I can take my formula, 1 over 1 minus x squared, but replace the x with a sine. So I get 1 over 1 minus sine squared of x. But now to finish up my chain rule, I have to multiply by the derivative of my inside function. Derivative of sine is cosine. Now that right there is technically the answer, but we can simplify it a little bit more. Do we know what 1 minus sine squared is equal to? We should. It's cosine squared. That comes from sine squared plus cosine squared equals 1. So this whole thing is equal to cosine of x over cosine squared of x using that Pythagorean identity. And this simplifies to 1 over cosine of x. But 1 over cosine of x is equal to secant. So my fully simplified answer is this is equal to secant of x. So we got that just by using a chain rule and the definition of the derivative of the hyperbolic tangent inverse, and then using a Pythagorean identity to help us simplify. Let's do another example. Differentiate the function f of x equals x times the hyperbolic sine of x minus hyperbolic cosine of x. Now notice, if I'm going to take the derivative of this, to take the derivative of x times the hyperbolic sine, I need to use a product rule from Calc 1. So my product rule says that the derivative of a product is the first guy times the derivative of the second, plus the second guy times the derivative of the first. So the derivative of the hyperbolic sine was hyperbolic cosine, and the derivative of x is 1. And now I just have to have the derivative of minus hyperbolic cosine, which is going to be minus hyperbolic sine. So what I get is x times hyperbolic cosine plus a hyperbolic sine and minus a hyperbolic sine. So those disappear and we just get x times hyperbolic cosine of x. Not too bad as long as you remember your rules from Calc 1. All right, so now since this is a Calc 2 course, you know that we're going to have stuff involving integration. So let's do a couple of integral problems. Evaluate the integral from 0 to 1 of 1 over a square root of 1 plus x squared dx. So take a look at that right now. That 1 over the square root of 1 plus x squared, that was the result of one of the derivatives of our hyperbolic inverse functions. In fact, it happens to be the hyperbolic sine inverse. So I know the antiderivative of that 1 over square root of 1 plus x squared is hyperbolic sine inverse of x. And I need to evaluate this at 1 and 0. Now you would think, well, just plug in a 1 and plug in a 0 and we're done, but we can do better than that. Because the hyperbolic sine inverse, we defined what that was. It was natural log of x plus square root of x squared plus 1. And we need to evaluate that at 1 and at 0. When I plug in the 1, I'm going to get the natural log of 1 plus a square root of 1 squared plus 1, so square root of 2, minus natural log of, it would be 0 plus the square root of 0 squared plus 1. That's a square root of 1. And we can simplify this a little bit because over here, this is natural log of 1. Natural log of 1 is equal to 0. So my final answer, simplified as much as I can get, is just natural log of 1 plus the square root of 2. All right, let's see. I still have 2 more examples to go. So this next example is going to show us how, even with hyperbolic functions, you might still have to do substitution sometimes. So our example, let's find the integral of hyperbolic secant squared over 2 plus hyperbolic tangent of x with respect to x. Now that looks pretty terrifying, to tell you the truth, but we can handle this because we know how to do substitution. If I let u equal the entire denominator, 2 plus the hyperbolic tangent of x, well then du is the derivative of this. Derivative of 2 is 0. Derivative of the hyperbolic tangent is hyperbolic secant squared, and dx, which means my dx is a du divided by a hyperbolic secant squared. So now if I plug that information into my problem, what we had our integral of hyperbolic secant squared. We're saying the denominator is u, and my dx is du over hyperbolic secant squared. And notice that the hyperbolic secant squareds will cancel out, and now we'll have just an integral in terms of u. Integral of 1 over u du. Now, what is that? Well, the antiderivative of 1 over u is natural log of absolute value of u, plus our constant. And then all we have to do to finish it up is plug our u back in. U was 2 plus the hyperbolic tangent of x, plus our constant. So there you go. You can still use u substitution even when working with these strange hyperbolic functions. Let's finish up with one more example where we're going to use u substitution again. And we're also going to do a definite integral. So our last example, let's evaluate the definite integral from 0 to 1 of 1 over a square root of 16 t squared plus 1 dt. Now, if you take a look at this, the 1 over square root of 16 t squared plus 1, it looks kind of like one of our formulas from the derivative of the inverse hyperbolic functions, but not quite. It kind of looks like the 1 over square root of x squared plus 1 formula, but it's not quite there. So let's first notice that I can rewrite this as 1 over a square root of 4t in parentheses squared plus 1 dt. Notice that's the exact same thing. And the reason I'm doing this is because I'm trying to rewrite this so it looks like one of my derivative rules, so then I can just do it backwards to get the antiderivative. Now that I have it written this way, if I let u equal 4t, then I would have a square root of u squared plus 1, which we can find using the derivative rules for the inverse hyperbolic functions. So if u is 4t, then du would be 4 dt. So dt would be du over 4. And let's go ahead and change our bounds. When t is 0, we'll get u equals 4 times 0, which is 0. And when t is 1, u will equal 4 times 1, which is 4. So let's rewrite this integral with our new bounds and our new variable. Instead of having bounds from 0 to 1, I now have bounds from 0 to 4. I have 1 over a square root of u squared plus 1, and my dt was du over 4. So now I can kick my constant outside, so that's a 1/4 that can come out. Integral from 0 to 4 of 1 over square root u squared plus 1 du. And now we can find the antiderivative of that 1 over square root of u squared plus 1. using that whole list of formulas we had for the derivatives of our inverse hyperbolic functions. We'll see that the antiderivative of this would be a hyperbolic sine inverse. So I have my 1/4 hyperbolic sine inverse of u, and my u is from 4 to 0. But just like one of the earlier problems we did, we know more about hyperbolic sine inverse than this. I can rewrite this as a natural log using my definition of the hyperbolic sine inverse. So plugging in my definition, I get 1/4 times the natural log of u plus the square root of u squared plus 1. And we're plugging in a 4 and a 0. So when I plug in the 4, I get natural log of 4 plus a square root of 4 squared plus 1, which would be a square root of 17. And then I have minus 1/4 natural log of 0 plus the square root of 1. We'll take a look at that second natural log over there. That's a natural log of 1, which is 0. So the most simplified I can get is 1/4 natural log 4 plus the square root of 17 as my final answer. And there we go. So these problems aren't too bad if you have those derivative rules memorized. Then you can do the antiderivative by just doing the rules backwards. However, if you're kind of like me and don't really like memorizing a lot of things, hang in there, and in a couple sections we're going to learn a technique that you can use that would allow you to find these antiderivatives without even having that rule memorized in the first place. So either way is fine. In my class, at least, you can either have them memorized and just regurgitate what you have memorized, or you can learn the technique in a couple sections and just derive the formulas on your own whenever you need them. If you have any questions, feel free to drop them below, or if you're a current student of mine, you can also email me or come to office hours and we can go over your questions there. And that's all I have for you today. I'll see you next time when we get to move on to some more of our integration techniques. Pretty soon we're going to be learning integration by parts, trigonometric substitution, partial fraction expansions, lots of fun stuff coming up. So I hope to see you in future videos.